Welcome back. This is it, the final part of our deep dive into digital imaging. Over the last few parts, we built the entire imaging chain, from photon to picture. We explored CR and DR technologies, and we really mastered spatial and contrast resolution. But now we face the third pillar, and you could argue it's the most clinically impactful one of all: noise.
You know, this quote from Dr. Jafar just nails it. It perfectly sets the stage for what we're talking about today. We've spent all this time sharpening the radiologist's eye with resolution, right? But what good is a sharp eye if you're trying to see through a thick fog of noise? Or worse, getting tricked by a mirage, an artifact that looks like something real.
And let's be absolutely clear about what's at stake here. This is not just some academic concept for physicists. When an image is so grainy, what we call quantum model, that it hides a tiny 3mm lung nodule, that's a misdiagnosis. That means noise is a fundamental patient safety issue. It's the invisible enemy we're always fighting. Okay, so how are we going to tackle this invisible enemy? We've got a solid battle plan. First, we're going to define the problem of noise itself. Then, we'll get to know our enemy by looking at its 4 different faces. After that, it's all about strategy, how to win the critical signal-to-noise ratio battle. We'll also cover how to navigate exposure indicators and artifacts on the battlefield. And finally, we'll bring it all together with the unifying triangle of image quality. Let's dive in.
So let's get right to the heart of the problem. You need to think of every single image we create as a kind of broadcast. We're trying to tune into a very specific channel. That's the signal, the useful information we need for a diagnosis. But that signal is always competing with static, right? And that static is the random, unwanted stuff we call noise. The stronger our signal is compared to that static, the better our diagnosis will be.
And that brings us to this, the fundamental trade-off that we can never, ever escape: the signal, noise, dose, triangle. These 3 things are permanently linked. If you want a beautifully clear image with less noise, you need more signal. And more signal means a higher patient dose, period. If you want to lower that dose, which we always do, you have to accept more noise, and that could compromise the image. So our job is to find that perfect balance, always guided by the Alara principle, as low as reasonably achievable.
Okay, so to fight this enemy effectively, we need to know its different forms. See, noise isn't just one single thing. It actually comes from several distinct sources. So let's deconstruct the enemy and meet the 4 faces of noise. First, and I mean this is the big one, the main event, is quantum noise. This is the dominant source we're battling in our day-to-day work. Then you have electronic noise, which just comes from the hardware itself. Third is structured noise, which is caused by tiny imperfections in the detector. And finally, there's a totally different beast called anatomical noise, which isn't a system flaw at all. It's just the patient's own anatomy, like ribs getting in the way of the lungs.
So what exactly is this quantum noise? Well, even with a perfect X-ray machine, the photons don't arrive at the detector in a perfectly even stream. They arrive randomly, kind of like raindrops on a pavement. That random statistical variation in how many photons hit each pixel is quantum noise. It's a fundamental property of physics itself, not a flaw in our equipment.
And this is the mathematical key to the whole thing. If on average a pixel detects n photons, the noise in that pixel is simply the square root of n. That means our all-important signal-to-noise ratio, our SNR, is also the square root of n. This one simple relationship governs pretty much everything we do to manage and fight noise. All right, so we know our main enemy, and we know its mathematical weakness. So let's shift gears and talk strategy. How do we actually win the battle for a better signal-to-noise ratio in the real world? And just as importantly, how do we avoid the common traps they love to put on exam?
Okay, if you only remember one thing from this entire discussion, make it this. Because your SNR is tied to the square root of the dose, if you want to double your image quality, to double your SNR, you have to quadruple the radiation dose. Just let that sink in. It is not a one-to-one deal. Improving image clarity is incredibly expensive when it comes to patient dose.
This is why it is absolutely crucial, especially for an exam, to know the difference between things that genuinely improve SNR and things that just change how the image looks. Increasing your MAS or using a detector with a better DQE actually captures more photons, giving you a better raw signal. But the common traps, like amplifying the signal or just narrowing your display window, they don't help at all. They just make the noise you already have more obvious. Okay, so we've talked about the fog of noise. Now we have to turn our attention to the mirages, those pesky image artifacts. They can be just as dangerous and misleading. But before we can even hunt for an artifact, we have to ask a more basic question. Do we even get the exposure right in the first place?
And that brings us to exposure indicators, specifically the S number. Now listen up, because this is so important and completely counterintuitive. The S number is inversely proportional to the dose. A low S number, like 100, means the detector got blasted with a high dose. A high S number, like 400, means a low dose. You just have to burn that into your brain because it's the opposite of what you'd expect.
So here's a classic exam-style question that ties this all together. If you're comparing two images, one with an S number of 100 and one with 400, what's the difference? Well, the S100 image got 4 times the dose. And because SNR is the square root of the dose, it has double the signal-to-noise ratio. See how it all connects?
Now, let's talk about those mirages. Artifacts can pop up from anywhere. They can be patient-related, like someone moving during the shot. Some are specific to the tech, like ghost images on an old CR plate that wasn't erased properly. Others are unique to DR detectors, like dead pixels. And then you've got the general stuff, like grid cutoff, that can happen with any system.
So when you see something weird on an image, don't just panic and guess. Use this simple framework. First, ask yourself, could this have something to do with the patient? If the answer is no, then ask, could it be the detector? And if not that, is it maybe something in the software or processing? This systematic approach helps you figure out what's going on and what to do about it. Fast.
All right, it's time for the grand finale. Let's bring everything we've talked about home. We're going to connect the dots between noise, which was our focus today, resolution, which we covered last time, and that constant factor, patient dose. These things don't live in separate worlds. They are all part of one single unifying concept. And here it is. This is the law of the land in medical imaging. You cannot optimize all 3 of these things at the same time. It's impossible. They are locked in a permanent trade-off. You want to improve resolution with smaller pixels? Great. But you're either going to get more noise or you have to crank up the dose. Want to reduce noise? Fine. Be prepared for lower resolution or, again, a higher dose. Every single protocol we choose is a compromise within this triangle.
So you might be wondering, why are we so obsessed with this SNR number? This is why. The Rose criterion is what connects the physics of noise to the actual practical reality of what a radiologist can see. It basically says that for the human eye and brain to reliably spot something, its signal has to be at least 3 to 5 times stronger than all the background noise around it.
So this is our target. This little number range, an SNR of 3 to 5, that's the finish line. That's the victory condition in our battle against noise. Every single technical choice we make, every protocol we design is all about one thing, pushing the signal of whatever we're looking for above this critical threshold so we can actually see it.
And with that, we've done it. We have officially completed our 4-part deep dive into digital imaging. We have followed the process from the photon leaving the X-ray tube all the way to the final image on the screen, and in the process, we've mastered the 3 fundamental pillars of image quality: spatial resolution, contrast resolution, and today, noise.
But we're not done yet. I hope you'll join me for the next part of the Radiology Physics series, Lecture 6, where we're going to build on this foundation and explore all the other factors that can make or break your final image quality.
So I'll leave you with this final thought from Dr. Jafar. Digital imaging transformed radiology from chemistry to computation, where every pixel tells the story of precision, dose, and diagnostic power. We've truly moved beyond the old days of film and chemicals into a world of pure information. Understanding that information is the key to everything we do. Thanks so much for watching.